We are gathered here today to evaluate this absolute beast of an integral. I mean, just look at it. It's simply ridiculous. We have the integral from 1 to infinity of the square of the sine of the natural logarithm of x divided by x squared times the square of the logarithm of x. So yeah, there is a lot of stuff going on here. And we're going to evaluate it using Feynman's technique. So let's call the integral here I, so we have something to refer to. And before we define the integral function, I'd like to perform a substitution to get a nicer structure. And what I'm talking about is letting the natural log of x equal u. Now, this implies that x equals e to the u, and this further implies that dx equals e to the u du. So that's how the differential element transforms. And what about the limits of integration? Well, as x approaches 1, u, which is the logarithm of x, will approach 0, correct? And as x approaches infinity, u will approach infinity as well. Okay, this is cool. So that means our integral I in the u world is the integral from 0 to infinity of the square of the sine of log x, which is now u, divided by x squared, which is e to the u squared, so that's e to the 2 times u, times the square of the logarithm of x, which is u squared, and the differential element transforms into e to the u du. So I can perform some simplification using these exponential functions here. So we have e to the u times e to the negative 2u, so we can write this as the integral from 0 to infinity of e to the negative u times the square of the sine of u divided by u squared du. And because u and x are just dummy variables, we can rename all of the u's back to x. So this implies that we're interested in the integral from 0 to infinity of e to the negative x times the square of the sine of x dx by x squared. Now that we have this nice structure, we can define our integral function I of some parameter, let's call it t. So where exactly do we place the parameter t? A nice choice here would be as part of the argument of the exponential function. So we have e to the negative tx times the square of the sine of x divided by x squared dx. And our target case here is that of t being equal to 1. That will give us our target integral I. And let's define t here to be a non-negative parameter. And that will come in handy later. For now, we have to differentiate the integral function with respect to the parameter t, and now the golden question. Can we switch up the order of the differentiation and the integration operators? Well, we have a bounded function in the square of the sine of x times this damped exponential function. And we have 1 by x squared, which is, again, a decreasing function on this interval of integration. So there are no problems regarding boundedness or convergence. So indeed, we can perform the switch up. And because of the switch up, the total derivative with respect to t becomes a partial one. So we have the integral from 0 to infinity of the partial derivative with respect to t of e to the negative tx times the square of the sine of x divided by x squared dx. And because we're differentiating partially with respect to t, that means all the x terms in the integrand are just constant. So we have the square of the sine of x divided by x squared, and differentiating with respect to t here gives us e to the negative tx, and because of the chain rule, you have this extra factor of x here as well. So one of the x's cancels out quite nicely, and you're left with the derivative of I with respect to t being equal to the integral from 0 to infinity of e to the negative tx, with a negative sign over here as well, an extra negative sign, e to the negative tx times the square of the sine of x divided by x dx. And it would be quite handy if we can get rid of this x in the denominator as well. And that's no problem whatsoever. All I have to do is differentiate again with respect to t. So that will give us the integral from 0 to infinity of, again, the square of the sine of x, and x being constants, e to the negative tx again, and another factor of negative x. So this cancels out with the x quite nicely again. And we have two negatives that give us a positive sign. So yeah, everything's falling into place quite nicely here. So the second derivative of I with respect to t equals the integral from 0 to infinity of e to the negative tx times the square of the sine of x dx. Take a moment to appreciate the fact that we started off with an absolute mess of an integral containing sines and logarithms, and now we have this really nice structure involving just a damped exponential term and a squared trig function that can be simplified, and this structure can be simplified further. I mean, you have the square of the sine of x, right? And 1 minus twice the square of the sine of x equals the cosine of 2x. So this implies that the square of sine x equals 1 minus the cosine of 2x divided by 2. So this implies that the second derivative with respect to t equals 1/2 of the integral from 0 to infinity of e to the negative tx times 1 minus the cosine of 2x dx. And just multiplying out the exponential term here and using the linearity of the integration operator, we have 1/2 times the integral from 0 to infinity of e to the negative tx dx. And this is pretty easy to evaluate, right? I mean, this sorts out to e to the negative tx divided by negative t, with the limits being 0 and infinity. And as x approaches positive infinity, e to the negative tx approaches 0. And as x approaches 0, e to the negative tx approaches 1, right? So you have a structure sorting out to 0 minus 1, and you have this big old negative 1 by t being multiplied as well. So that gives you a 1 by t structure. Okay, so let's just rewrite all of this as 1 by t. And let me just erase all of this to give myself some writing space. And there we go. All right, and we have a negative sign, integral from 0 to infinity e to the negative tx times the cosine of tx dx. And this is pretty simple to evaluate as well. Let's just take a moment to figure out what exactly it sorts out to. So let's call our integral I sub 1 as the integral from 0 to infinity of e to the negative tx times the cosine of 2x dx. And now to invoke Euler's wonderful formula, which states that e to the ix equals the cosine of x plus I times the sine of x. And this implies that the cosine of 2x equals the real part of e to the 2ix, right? And the nice thing here is that we can replace if we replace the x by a negative x, then because the cosine is an even function, the negative sign doesn't matter here. And although that alters the imaginary part of the right-hand side of the equation, that doesn't matter, right? Sine function is an odd function, so you can pop out a negative sign, and this does not matter here because we're only interested in the real part. So the real part of e to the negative ix and e to the ix are exactly the same. So I'm just going to introduce an extra negative sign here as well, to multiply out two exponential functions with negative arguments. It makes the complex number algebra a lot nicer. You'll see what I mean. So this implies that we can write I sub 1 as the real part of the integral from 0 to infinity of e to the negative tx times e to the negative 2ix dx. And multiplying out the two exponential functions gives me the real part of the integral from 0 to infinity of e to the negative x times t plus 2i. There you have a plus sign between the numbers in the argument here. That seems nice. The simple pleasures of the casual integral lover. Anyway, so performing the integration gives us the real part of the limits of integration being 0 and infinity, and we have e to the negative x times t plus 2 times I divided by negative t plus 2 times I. And if we expand the numerator here and write this as e to the negative xt times e to the negative 2ix, the complex exponential is a bounded function. However, this is the real exponential function, and it's a damped one. So as x approaches infinity, this term here will approach 0. So the first term here just cancels out, just crosses out to 0. And for the limit as x approaches 0, we have e to the 0 times e to the 0, which is, again, 1. And we have a negative sign here because we have to subtract the results of the upper limit and lower limit, so that cancels out the other negative sign quite nicely. So yeah, this is what we're interested in. We're interested in the real part of 1 by t plus 2 times I. And we can do that, we can extract the real part by just expanding using the complex conjugate. So multiplying out by t minus 2i upstairs and downstairs. This gives me t minus 2i divided by t squared minus 4i squared, and I squared is, of course, negative 1. So we have t squared plus 4, and this implies that I sub 1, which was the integral from 0 to infinity of e to the negative tx times the cosine of 2x dx equals t divided by t squared plus 4. Okay, cool. So plugging in this result into our result for the second derivative of I with respect to t, which I've just copied down here because, well, I needed writing space. So this gives us 1/2 times t, so that's 1 by 2t, minus 1/2 times t divided by t squared plus 4. Okay, cool. And now we plan to recover back our integral function from the derivative, the second derivative in this case. So just integrating the second derivative with respect to t gives us the first derivative with respect to t, and which is equal to the antiderivative of the right-hand side of the equation, is in fact 1/2 times log t minus 1/2. In fact, you're going to need another factor of 2 here as well. So let's just write this as 1/4 times all of that stuff. So that sorts out to 1/4 times the logarithm of t squared plus 4. Plus, of course, a constant of integration c that we're now out to calculate. And let me just move this a bit. Yeah, so we can give the constant of integration some breathing space. Okay, cool. So how exactly do we figure out the value of the constant of integration? Well, for that, I have to recall the structure of the derivative of I with respect to t, which we remember as the negative of the integral from 0 to infinity of e to the negative tx times the square of the sine of x divided by x dx. And this damped exponential term is quite useful over here, because in the limit of I of t, as t approaches infinity, this thing here approaches 0. So the entire structure just collapses to 0 in this limit. So this implies I'm going to need to do some simplification on the right-hand side, which is no problem whatsoever, Just give me, again, a minute to not copy and paste. God damn it, I wanted to delete this. Yes, delete. Off with you. And let me perform some clever math now. So we can write this here, 1/2 of log t, we can write this as 1/4 of the log of t squared. And using the properties of the logarithm, after factoring out a 1 by 4 term here, we have log t squared minus log of t squared plus 4, right? So again, using the properties of the logarithm, I can just write this as a combined logarithm of t squared divided by t squared plus 4. And now I can apply the limit without any stress whatsoever. So on the left-hand side, you have the derivative of I with respect to t, and applying the limit as t goes to infinity. So the left-hand side is 0, and as far as the right-hand side is concerned, the limit of t squared by t squared plus 4 as t approaches infinity, if you multiply upstairs and downstairs by the reciprocal of t squared, you get the limit as t approaches infinity, and once again a poor choice in terms of writing space. So you have the limit as t approaches infinity of 1 by 1 plus 4 by t squared, correct? So this sorts out to 1. So you have the logarithm of 1, which is 0, right? So this implies that you have 0 equal to 0 plus c, which implies that c conveniently equals 0. Yeah, I absolutely love it when this happens. So yeah, this was nice. That was pretty damn nice. So this implies that the first derivative of I with respect to t equals 1/4 of the logarithm of t squared divided by t squared plus 4, where I've retained this really nice structure here. And the constant of integration was 0, so yeah, we're home free. Next up, I plan to recover back the integral function I of t, and that means I have to integrate again with respect to the parameter t. Okay, cool, no problem whatsoever. So on the left-hand side, you have I of t, and on the right, you need integration by parts. So you have 1/4 times, I'm going to differentiate this bad boy here, this loggy boy here, and I'm going to integrate 1 with respect to t. So that gives me t times the logarithm of t squared by t squared plus 4 minus the integral of t times the derivative of this logarithmic term. So the derivative with respect to t of log t squared divided by t squared plus 4, where again I can simplify things quite nicely or make the differentiation much more efficient by just using the properties of the logarithm, right? So we have a bunch of stuff here, and we've got 2 by t minus 2t divided by t squared plus 4. And all of this is supposed to be multiplied by this factor of t as well, right? So we have 2 minus 2 times t squared divided by t squared plus 4 dt. And some simplification is in order here for the integrand. So this can be written here as, well, if you multiply this by 2, you have 2 squared plus 4t. No, 2 squared plus 4, because you only had a t squared plus 4 and a 2, minus 2t squared. So that cancels out quite nicely, and you're left with t squared plus 4 here as well. Okay, that was nice, but no, wait. I have an 8 here, right? I have an 8 here. So yeah, that's perfectly normal, doing complex problems in integral calculus and, messing up basic arithmetic. This is perfectly normal. And it's cool. It's a sign that you're actually good at this stuff, I guess. So yeah, I should just probably move on. So we have 1/4 of t times log t squared divided by t squared plus 4 minus 8 times the integral of 1 by t squared plus 4, which we recognize as the familiar arctangent boy, where this can be written as 2 squared, so we can just write this as evaluating out to 1 by 2, so that's 8 by 2 times the inverse tangent of t divided by 2. Okay, nice, and we have some nice cancellation here as well. And multiplying out the 1 by 4 gives us 1/4 of t times the logarithm of t squared divided by t squared plus 4 minus 4 by 4 is just 1, so we have the inverse tangent of 1/2 plus the constant of integration c. So we have another constant of integration to evaluate, and this time I need to recall the structure of our actual integral function I of t, which we defined as the integral from 0 to infinity of e to the negative tx times the square of the sine of x divided by x squared dx. And if I plug in t being equal to 0, we're left with the integral from 0 to infinity. This thing evaluates to 1, so we have sine squared by x squared dx. And this is just one of the Dirichlet integrals, right? And this evaluates out to pi by 2. Link in the description if you're not familiar with this result. So using t equals 0, we have on the left-hand side pi by 2 equal to 1/4 of, now what about this? Well, in the limit, and this is probably where I should just use a limit operator in this case. Yeah, that would make it much better. So this is the limit of I of t as t approaches 0. Sorry about that. And this limit evaluates out to pi by 2, right? Everything makes sense because the limit of e to the negative tx as t approaches 0 is, of course, 1. So again, we have this result. This result is preserved. And now on the right-hand side, I have to deal with the limit as t approaches 0 of t times the logarithm of t squared by t squared plus 4. And you can verify using L'Hopital's rule that this limit evaluates out to 0, which is, again, quite nice. So we have 1/4 times 0 minus the inverse tangent of 0 is, again, 0 plus c. So, again, we have a nice result for the constant of integration. It just evaluates out to pi by 2. So replacing c with pi by 2, and again giving myself some writing space. Finally, now evaluate our target case, which is the case of t being equal to 1. So I of 1, which is our target integral I, equals 1/4 of 1 times log 1 by 1 squared plus 4 is 5, minus the inverse tangent of 1/2 plus pi by 2. Okay, cool. And we can actually simplify this further if I take this part of the expression and write this as negative pi by 2 minus the inverse tangent of 1/2, because there's this very nice property of the inverse tangent function that the inverse tangent of z plus the inverse tangent of negative 1 by z equals pi by 2. So this implies that the inverse tangent of 1 by z equals pi by 2 minus the inverse tangent of z. So just substituting 1 by z equals 1/2, that is, just substituting z equals 1/2, we get the inverse tangent of the reciprocal of 1/2, which is, of course, the inverse tangent of 2. And wait a second, there was a plus sign. Yeah, this is a plus sign. So we have the inverse tangent of 2 here. So finally, we may summarize our results as our target integral I being equal to the inverse tangent of 2 plus 1/4 of the logarithm of the reciprocal of 5, which is quite a nice result indeed, and a pretty nice journey of integration, if I say so myself. So I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.